So this is lecture 4, and today is 7th of April 2021. Okay, so let's see where we are. Last time, to summarize, we showed you how you can derive the equation of motion for a single degree of freedom undamped system, which is freely vibrating. And this is what basically describes the model that we have set up, okay? And of course, we solve this equation for the sole purpose of showing you that this is a sinusoidal motion, and the frequency of this freely vibrating system, we call that natural frequency. Of course, there was an alternative form. We wrote this equation. And as we, of course, showed you that in order to solve this problem, you need some initial conditions at, say, some times, like time equal to 0 for the velocity and the displacement. But nevertheless, the whole intention was to introduce to you one of the most important dynamic characteristics of a system, which is omega n, natural frequency. So as I promised, we are going to spend about 2 weeks to show you that how we can actually set up this simple model for any complex or relatively complex dynamic systems. So we want to discuss about the modeling. The approaches that I consider, in fact, are 3 different approaches in order to accomplish this objective. I will first show you that if the structure is simple, we can simply use the second law of mechanics, which basically results in what we do is set up the free body diagram. And if you use the lumbar force, which I do, instead of just inertial force, in other words, the inertial force which is placed in the opposite direction of motion, you have basically a static problem. And by writing the setting up the free body diagram and using the second law of mechanics, writing summation of forces equal to 0, you can set up the model and find the natural frequency. That's one approach. If the problem is a little bit more complicated, or actually as part of that approach, you see that it is sometimes easier to simply try to find the stiffness component. You see in this equation, in this formulation, in this modeling, the most really important part is to define K, because math is relatively easy, is almost identifiable in most cases. It is a stiffness. So in the second approach, in many cases, we can demonstrate that if we use a definition of the stiffness, what is the stiffness? A stiffness is a force to generate, or the force that generates a unit displacement. Has nothing to do with the dynamic motion. It is a static quantity. You've seen that in the strength of materials and so on, that by using a simple structural analysis, that is using a force that generates a unit displacement, you can easily find the stiffness in a system. And if you find the stiffness, you can then set up easily the equation of motion, okay? The third approach is for more complex cases. I call them complex systems that you can still use these two approaches, but it may be very, very difficult to do that. Is if the structure is conservative, that is, we do not have a damping or the energy dissipation in the system. What is a conservative system? That it does not dissipate or gains energy as it goes through a motion, right? We know that the concept of conservation of energy tells us that sum of kinetic and potential energy is always a constant. So that means this sum doesn't vary with time, or its derivative with respect to time is zero. So we can use this approach to set up the equation of motion. I will demonstrate all these three approaches through some example problems. I see that there are some questions in the chat. Let me see what these questions are. Would anyone be able to share a link to the textbook? Yes, please answer that. Thank you. So that question has already been answered. All right. So let me first start showing you how we can use this approach through a few simple problems. I will start with a few problems, starting with some simple one and a little bit growing to more complicated one. Let's say you have a disk with a mass m connected to a shaft, and this disk is subjected to a time-dependent torque, and we want to find the equation of motion for this, or rather set up this model for this structure. I told you any structure can be modeled by this single degree of freedom system, and that's what we want to do. In order to do that, we need to identify what is K and what is M. So let me call this equivalent mass and equivalent stiffness. So the first approach that I'm going to apply is second law of mechanics. What does that mean? This shaft obviously has some geometric and material properties given: shear modulus of elasticity, polar moment of inertia, of and the length and the diameter, and so on. Okay. So in order to do that, as I said, we use simply the free body diagram. So this disk is subjected to this time-dependent torque. Its motion is resisted. It is going through some deformation. And in other words, the shaft is going through some deformation. I call that angular deformation phi. Okay. So if the shaft experiences a deformation phi, it is the deformation of the shaft that is resisting the motion of this disk. In other words, the shaft represents a torsional spring, which we will find that, of course, resisting this rotation. So that is a force or moment that is resisting the motion. And then, of course, we have the motion. This is a mass. So we need to also use the lumbar force here that is in the opposite direction of the motion, and this is the free body diagram that we were looking for. Okay, remember, if you have a disk, okay, with the radius r, mass m, I is simply what is 1/2 mr squared. Okay, so using this free body diagram, okay, I just simply write summation of all forces, in this case moment, equal to 0. What do I have? I have I phi double dot, okay, plus kt times phi, the stiffness force of the shaft, is equal to the applied load. Okay. So we know what I is. I said that I is easily detectable, which is this. But what is this torsional spring? Remember, we can use the concept of the definition of the stiffness. From the strength of material, you remember, if you have a load acting on a bar of length L, area I, modulus of elasticity E, the delta or deformation that this bar experiences was what? PL over AE. Okay. So, what is the definition of a stiffness? Force that causes a unit displacement. In other words, if this is one, this would be K. So, in this case, K would be AE over L for a bar. How about for a shaft that is subjected to a load like this, and these are the parameters that we have. And so if this shaft is experiencing a deformation theta, if you don't remember the formula, use an analogy here. For P, you put instead the torque. For L is the same as that. A is replaced by the polar moment of inertia of the shaft, and E is the shear modulus. So this is the relationship between the angular deformation of the shaft and the applied load. So the stiffness is the force that causes a unit displacement. So if this is one, this would be the torsional spring. So the torsional spring is GJ over L. Okay? So in this equation, then, what do you have? You have 1/2 mr squared plus GJ over L times phi, this is phi double dot, is equal to T of T. So compare this equation with mu dot plus Ku is equal to F. M equivalent is this, and K equivalent is this. So if you want to find the natural frequency, this is K, this is M. So natural frequency would be what? G J L over 1/2 M R squared. You can simplify this, of course, if you want further, but this is a good example showing you that if you have a complicated problem, how you can actually, um, using the second law of mechanics, set up the equation of motion and find the natural frequencies and uh, the model for this system. Any question? If not, let's do another
Uh,
problem.
sorry, what was I like I equals 1/2 mr squared? What is that?
You remember from in dynamics, if you have a disk, if you have a disk rotating about its center and the radius is r, okay, the inertia force, force of inertia, moment of inertia, which is I, is what? Is 1/2 m. If this has a mass of m rotating about its center, its moment of inertia was this, if you recall from dynamics.
Okay, thank you.
Sure. All right. So let's do another problem. Let's consider another example. Okay. In this case, let's say you have a rigid bar which where you have a mass, lumped mass attached to the tip of that. At this end, it is supported by a pin, and somewhere in the middle of this bar, you have, not in the middle, but at some distance a, lowercase a from this tip, you have a spring that is acting at a support, and this length from here to here is B. In other words, length of this beam is L, A plus B. This is a rigid, massless beam. And you want to, again, set up this model. That's the whole intention, to find this model. And of course, the sole purpose of that is to find a natural frequency. So we are going to demonstrate again using the second law of mechanics, how you can find the equation of motion or set up this model basically for this system and find a natural frequency. Okay. So if this beam is going to experience oscillations, let's say at some point where the beam has deflected downward like this, okay, we look at its equilibrium, dynamic equilibrium. So what forces you have? To have forces at the support, you do have a force due to the spring that is resisting this motion. And then you have the inertial force, okay, due to rotation of this mass, which I would put it this way. I call that the lumbar force, I theta double dot. So this represents a free body diagram. You just need a few pieces of information here. The displacement that this spring is going to experience, or in other words, this displacement, I call that delta A. If this angle of rotation is theta, this would be A times sine theta. However, if theta is very, very small, okay, sine of theta, you remember sine of theta and cosine of theta. When theta is very, very small, sine of theta is theta, cosine of theta is 1. So I can approximate that this way. And so this is the free body diagram. Therefore, I use the second law, and summation of moments about A is equal to 0. If the lumbar force is put this way, this is a static problem. So add up all the forces, a moment, I theta double dot, okay, plus moment of this force about point A. So F of K times A is equal to 0. Substitute for F of K, which is K times delta, and delta at A, which would be K times A theta. So this equation becomes, I would substitute for M, which is basically you have a lump mass rotating about a point. So this would be simply ML squared. Remember from dynamics, this is a moment of inertia of lump mass rotating about a point. So if you substitute for all those, you get ML squared plus KA squared theta is equal to 0. So again, compare this, oops, ML squared theta double dot, of course. Compare this with this equation, MU double dot plus KU is equal to 0, which is this for this model. You have been able to replace this structure with this model. So what I had claimed is true, that you can replace any structure with this single degree of freedom system. And of course, the most important part of that is what is K and M, which I call the K equivalent, mass equivalent. This is the mass equivalent. This is the K for this model, for this structure. So natural frequency, which is K over M, would be what? Would be K, square root of K A squared over ML squared, or it would be A over L square root of K over M for this structure. So you see, we could convert that structure into a single degree of freedom model that we had seen before. Any questions? If
Yeah.
not,
Professor?
yes,
Um, I was just looking at that. So for the initial free body diagram, I noticed, isn't the thing on the I theta double dot, isn't that an acceleration? The only reason
correct.
I'm asking is because we like in my past dynamics, we'd put that on the other side of the equation, so where the
Yes,
zero is,
yes.
but that
You
would
see what
change
I
the
do?
sign.
Exactly. Good point. You see what I do? I put the inertial force or inertia, rotational inertia in the opposite direction of motion. And we call that the lumbar force. If you do that, instead of having, let's say, summation of moments is equal to MA, summation of moment, summation of forces become equal to zero because you've already taken this to the other side of the equation. You see what I mean?
Okay.
So that's by using the lumbar force, which is in the opposite direction of motion, you have presumably, or sort of in a way, you have converted a dynamic problem to a static problem. Because if you put that force in the opposite direction of motion, that means system supposedly is not moving. You have already incorporated the inertial force in the opposite direction. So the bottom line is, if you put the inertial force in the opposite direction of motion, then you can write this. If you don't want to do that, you can write summation of moment about A is equal to I theta double dot. Same thing.
Okay,
Same.
so the difference, if I'm understanding, is you just flip the sign and keep it on the
Exactly.
same side. Okay, perfect.
Exactly.
Thank you.
Exactly. Exactly. That was a kind of a simple trick that D'Alembert introduced in dynamics in order to uh, be able to use same approach, writing three body diagram in the static, the way we do it in the static. That's it. Let's do another problem.
I actually have one more question. Sorry.
Sure, no problem.
Um, does the force of the spring act straight up or perpendicular
Yes,
to the body?
it is
The-
acting perpendicular to this, but the rotation is a small angle rotation. So you would assume that this is still perpendicular to the
Okay.
speed.
Okay.
Yes. So, so let's do another problem. Okay. So this is the problem I'm going to do here. Okay. Let's say now you have a bar, a rigid bar that is hanging from this point that is connected to, and a spring in an unstretched position like this is attached to it. The bar has a mass of m and a length of L and is like a pendulum, oscillates like this, and you want to find the equations of equilibrium or set up again this model for this structure so you can find the natural frequency. Okay. So this is what we have. In other words, this bar is oscillating like this. This is the angle of rotation. Remember again from dynamics, if you have a bar, and rotating about this endpoint, the moment of inertia for that is ml squared over 3. Okay. All right. So again, I want to set up the free body diagram. What is a free body diagram? This is, of course, I'm exaggerating with these angles. If this ball rotates this way, you do have the force of this spring resisting it. You do have these two forces, AY, AX, that comes from the connection. then you do have this mg force. And if this is moving that way, I put again, the rotational inertial force this way. So this is a free body diagram of this structure. You need certain quantities here. For instance, this distance, if which is basically the deformation that the spring experiences, is what? If this is L, this is theta, this would be L sine theta, assuming that theta is very small, this is L theta, okay? And this distance is L. So again, I simply write summation of moments about A is equal to 0. And from in this free body diagram. So I have I theta double dot plus f of k times L plus this distance would be L theta over 2. If this is in the middle, so if this is L theta, this would be L over 2. So the moment arm of this force would be L theta over 2. So you have mg times L theta over 2 is equal to 0. What is f of k? F of k would be k times L theta. And what was I? I was ml squared over 3. So substitute for all of these in this equation. I get 1/3 ml squared theta double dot plus k L squared theta plus mg L over 2. Theta is equal to 0, or let me uh, sum these up. I get 1/3 ml squared theta double dot plus um, k L squared plus mgl over 2 theta is equal to 0. So what have I done? I have been able to set up this equation, or in other words, I've been able to set up this model for this structure. If this is K, the equivalent K, which is the coefficient of the displacement, is this term, and the mass in this equation is the coefficient of the acceleration term. So if I want to find the natural frequency, would be simply K over M, or K equivalent over M equivalent. So that would be KL squared plus MGL over 2 divided by 1/3 ML squared. This is the natural frequency of this structure. Any questions?
Yeah, how come in this problem we included mg but not in the previous one?
Excellent, excellent question. See, what I'm assuming here, that the spring is in its unstretched form. You remember even the bonus problem that I gave you? If this is a spring, if you measure the displacement from the position where the spring has already gone through the static displacement, measure it from here, equation of motion is independent of the gravitational force. But here it is not the case. This is an unstretched form, so simply a bar is attached to it. So when it goes like this, mg shows up. Okay. All right. So let's do another problem. Okay. And also you have a combination of rotational and translational motion. Anytime you have those combinations, mg would show up. All right, so let's do another problem here. Okay, let's say you have, again, a rigid bar, but this time this rigid bar is under the action of a triangular load, the intensity of this load at the tip here is P0FT. We have a damper attached to this to this beam, rigid beam here, and a spring attached to it at this point. This distance is A. This whole length of this beam is L. This is again rigid, okay, beam, and a pin connection here. So we want to again set up, replace this structure with something like this. So what is the mass? What is the stiffness? And what is the, damping coefficient in this case? Okay. So again, let's set up the free body diagram. This is the beam. Let's say it's rotating up and down. Let's say I'm going to look at this position when the beam has rotated an angular displacement of theta t. You have these unknown forces. You do have an applied load, this triangular load, but you can replace, remember from statics or strength of material, I can replace this with an equivalent concentrated load, which its magnitude would be area under this triangle, right? So this is the base, this is the height of the triangle. So this load would be P0 FT times L over 2, area of this triangle. This is the load intensity, okay, which acts at a third of a distance from here. What else do you have? If this is going up, you do have a force of the spring downward. This is the deformation that spring experiences. Again, if this is theta, this would be A theta, small angle assumptions, and the displacement that the damper experiences delta C would be simply L theta. Okay, so this is the free body, and of course, you do have the force of the damper. And this is the free body diagram. And of course, I need to also consider the inertial force, which is I theta double dot. And now I have a complete free body diagram. I write summation of moments about A is equal to 0. You have I theta double dot, that moment of this force at a distance A, so would be Fk times A. Moment of this force with respect to A, which would be F of C times L. Then you have the moment of this force, which would be in the opposite direction, P0 Ft L over 2 times this distance, which is 2/3 L is equal to 0. So this is the equilibrium equation, right? Let's simplify that. F of K is K.
Professor,
Yes.
why wouldn't it be Fk times A theta if A theta is the displacement of that spring?
Correct. Yes, F of K is K times A theta. That's what.
Oh, I see. That's the moment arm. Sorry, got it.
Right.
Got
Correct.
it.
Yeah, that's correct. And F of C would be that C times the velocity, which is, this is the displacement. So velocity is the derivative of that. So would be this times L. Okay. So substitute for these in that equation. Okay. You get, and substitute for I also, which is again a bar rotating about its tip, would be ML squared over 3. If you put all these into that equation, you get ML squared over 3 theta double dot plus CL squared theta dot plus K A squared theta is equal to P naught L squared over 3 F of T, okay? And that's because this 2 and 2 cancel out. So this is the equation of motion. So again, look here. Compare that with mu double dot plus cu dot plus ku is equal to f of t, right? This is the mass equivalent. This is the damping equivalent. This is the K equivalent in this model, right? So you have converted this structure to that model where this is the mass equivalent and this is the stiffness equivalent. And that's all I need to find a natural frequency, which is what the problem has asked me to do. So this would be Ka squared over ml squared over 3. So this would be A over L square root of 3K over M. That is the natural frequency of this structure. Any questions?
Yeah, why don't we have to divide both sides by the P naught L squared over 3 to make it into the same form? So f of t is alone.
Well, all I need is to set up this equation, right?
Mm-hmm.
So I did not divide it by P naught. Did I?
No, you didn't.
No, I didn't. No, I don't, because that's the force. I don't divide it by the force.
Okay, well, it seems like I was just confused because you're also multiplying that by f of t.
Oh, no, the form of this is a little bit confusing. The force at this tip is a quantity P naught times some forcing function, time dependent function.
Okay.
That was the given force. Maybe the notation should be this: uppercase f of t is p0 ft. That's what confused me. In other words, this ft is that big ft.
Okay, cool. And then I was
Good
also
question.
confused about the signage for I theta double dot. It looked like it'd be in the negative direction.
See, I theta double dot is again the lumbar force. If this is going that way, the lumbar force always goes in the opposite direction of motion. So motion is that way, the lumbar force is this way. Inertial force is that way. The lumbar force is fictitious force we put in the opposite direction of motion.
Okay.
That's why they all have positive signs. Okay. So let's do yet another problem here. Okay. I have another problem that I've set it up here. Let's say you have a rigid bar again, but this case is massless, rigid bar. A mass of, lump mass is attached to this top. This beam is supported by a pin here, by a spring here. And this mass is kind of rotates like this, or a beam rotates like this. This height is B, this is A. So in other words, this system is rotating like this. Okay, this is the angle of rotation, theta. And we want to find again the equation of motion, or find the natural frequency by modeling this as something like this. Okay, again, let's set up the free body diagram. This is the original beam, okay, has rotated. So this is the rotated position. This angle is theta. This, of course, I have a gravitational force here. The displacement here, if this is A, this is B, this would be A theta, and obviously I have this force of the spring, these two forces again, and again, the inertial force, which I put it in the opposite direction, I theta double dot. The only I, moment of inertia, that comes into picture is due to this lumped mass rotating about this point. This is a distance is b, so this would be mb squared. Okay, so now let's take summation of moments, and this distance then would be b theta. So free body diagram, write again summation of moments about point A is equal to 0. So you have mg, which is this force, times this distance, b theta. You have then this inertial force, which is going the opposite direction, is mb squared theta double dot. Then you have this one, which is also f of k times a is equal to 0. F of k, again, would be k times a theta. So substitute for these in that equation and simplify that, you get mb squared theta double dot plus k a squared theta minus mgb theta is equal to 0. Further simplify that, I get mb squared theta double dot plus k a squared minus mgb theta is equal to 0. Again, look at this. This is m equivalent. This is k equivalent. So if you want to find natural frequency would be simply a squared k minus mgb divided by mb squared. However, this problem has a condition. This has to be positive in order to have a real natural frequency. That means a squared k has to be greater than mgb. That's the condition. Okay? All right. Any questions? So we covered a few example problems using the first approach, which is using the directly the second law of mechanics, free body diagram, setting up the equation of motion. Now, there are some special cases that instead of going through that pain when the system is a little bit more complicated, we can use the definition of stiffness and also the arrangement of the stiffnesses is such that we can use that approach to find the total of the stiffness in the system in an easier way. There are two special cases that I want to introduce, and it is discussed in your book. These two special cases are as follows. It happens that all stiffness components or elements in the structure experience, the arrangement is such that they experience the same force or subjected to the same force. Or there is another possibility or case that all the stiffness elements experience the same deformation. By mistake or traditionally, this situation is called springs in series. This is referred to springs in parallel. Let me emphasize, geometrically, the stiffnesses don't have to be in series so that the forces that they experience is the same. Or the same thing with the parallel case. Let me give you an example. This is a beam, a stiff, has a lump mass, and another spring is attached to the tip, and this beam is oscillating like this. Obviously, this beam represents a spring, right? This is one spring, this is another spring, right? What is this? These two springs are neither parallel nor attached in series. However, they experience the same deformation. If this beam goes down delta, this spring experiences the same delta. So these two are in parallel, orientation. So we use this concept to add up these. Or you may have something like this. In fact, this is an example in the book. Seemingly, these two springs are in series, right? Wrong. Because you do not know if these experience the same force. What you do know is as this mass experiences the displacement, both of these experience the same deformation. So although geometrically looking, they seem to be in series, but they're actually in parallel. So that's why it is important to emphasize parallel and series are meaningless terms. You need to look at if the structure, if the springs are such that forces are equal or they go through the same deformation. So let me introduce very quickly the case one. And I know I'm not going to do it justice here because I'm going too quick. On Friday, we complete both of them coverage, but at least let's show you quickly what is the objective here. The objective is if you have two springs experiencing the same force, we want to replace these with a single spring. It is always the case. We want to combine all the stiffness elements in a structure so that we find that equivalent spring. We did that already for some simple problems by using just setting up the equation of motion. But in many cases, it's not easy to do it that way. So we use our understanding of how these springs are oriented. If they're such that they experience the same force, the question I'm asking is it possible to say a single spring that experiences the same force can replace those two? If you find a spring like this, and this spring is subjected to a displacement like this, what would be the relationship between this and the stiffness and the displacement that this spring experiences? Would be K equivalent times U3 minus U1, right? Now look at each one of these two springs. K1 is subjected to the same force as this K2 is subjected to, right? But because the stiffnesses are different, the springs experience different deformation. In other words, this spring is relationship to the displacement that would experience would be U2 minus U1. This one would be K2 times U3 minus U2. Okay? I would rearrange these. I write that U2 minus U1 is F over K1. U3 minus U2 is F over K2. But look at here. I can write U3 minus U1 is F over K equivalent. And if you add these two, you see that U2 cancels out. You get F over K1 plus F over K2 is F over K equivalent. Or in other words, that single spring that you want to find that its stiffness is going to replace these two springs can be found from this relationship. I know I didn't do a good justice here. Honestly, I went through that in a rush. I'm going to start from here in the next class and go through several problems so that you can really grasp a good understanding of what is the meaning of parallel and series of spring or springs experiencing the same force or same deformation. Sorry for the rush. I'm going to stop here. And if you have any questions, we'll be happy to answer.